So in this series of videos we're going to take a look at some passive components, the resistor, the inductor and capacitor. We're going to see what their characteristics are with respect to the voltages and currents, and we're going to connect them together and derive some filter equations, and then eventually we're going to move on with some Laplace transforms that will allow us to analyze those circuits quite easily. So first of all, let's start with a resistor. So we have a voltage resistor, the resistor state as having an ohms value, so the resistor is in ohms, and there is a relationship, so we have this current I flowing through our circuit, and through Ohm's law we can say that there is a relationship RVI. Good way of remembering this, if we draw a little triangle here, you'll see this in many textbooks. If you want to calculate I, then it's simply V over R. If you want to calculate R, if you didn't know it but you're given the other values, then it's V divided by I. If you are given the resistor value and the current, then in order to calculate V, then we can say V equals R times I. So let's just write some of those out. Happy days, fairly straightforward, brilliant. Okay, so next, let's think of the voltage, and now let's place two resistors in the circuit. Okay, so we'll call that R1, this is R2, we have current I going down there, and a V. So let's think about some of the relationships here that we have. Well, we've got two resistors, and these two resistors are connected in series. So our series, simply what we do is we add the resistances together, so we can say R1 plus R2. What we can do then is, based upon these equations, we can recalculate the I. So it's simply, if we wanted to find I in this case, if we look up here, we've got I equals V over R. So it would simply be V divided by R series equals I. Okay, so if you're faced with that kind of problem, that's how you'd find the I in this case. Now, V, if we look here, if we consider this V out, I connected a little wire here, and I measure across these two resistors. Then what we can say, if we look across here, then we can see that the voltage here is going to equal the voltage at this point here. So if I measured across these two resistors, we can see just by inspection that we've got a voltage that is applied across these two resistors. So I could say that this point of voltage here is equal to this V. Now, if we're asked to find this voltage, so V, let's just call it VR2. So this is the voltage across this R2 resistor. And how can we do that? Well, there are a couple of methods. One is, we do know that if we consider this path of I is going to flow through both resistors, then this I is flowing through R1, I is also flowing through R2, and we know that the voltage can be found by R times I. So if you know I, then simply you could say that VR2 equals R2 times this I flowing through, which we've calculated as follows. So the I, it's important that you think about I being as a result of this series combination of these resistors. And when we do this, this is what's known as a potential divider. The reason being is we are dividing this potential V across these two resistors. So this will be the VR1. A good way of remembering this is to think about whichever resistor you are measuring. We call that the resistor of interest. And then we've got the total resistance in the circuit. And we can say, if in this case, if we want to rewrite this VR2, we could say VR2 equals resistor of interest, which is R2, divided by the total, which in this case is R1 plus R2. Okay, and if we multiply that by our voltage source V, this here is a classic potential divider type equation. Now it doesn't matter whether we replace one of these resistors with, say, an inductor or a capacitor. We just have to replace the associated resistor with a impedance, as it's called. So an imaginary impedance, and this is something that we'll look at as we move forward. And this is how we build filters that attenuate voltage levels as frequencies change.